Hi, I'm Mark. This is Paco. Sometime during the next 15 minutes, he will probably shit on my shirt. So in kinetics, the rate determining step is the step in a mechanism that has the biggest effect on the overall reactions rate. And it's usually identified as being the slowest step in a mechanism. And it's so much slower than the other steps. Oh, you want to go over there? Okay. So much slower than the other steps and has such a more significant impact on the overall rate compared to the others that what you usually see is that the rate law of the rate determining step matches the rate law of the overall reaction. And this can be a good way to experimentally verify that your mechanism is correct if you see the two rate laws match up. So for example, let's look at the reaction between NO and bromine to give you NOBr. And let's say we're thinking it's a two-step mechanism where NO converts to an intermediate into O2, and this intermediate reacts with bromine to give you NOBr. First thing, remember that the two steps should add up to give you the reaction you're looking at. Otherwise, you might as well not do anything else that we're about to talk about because you're looking at a completely different reaction. But here it checks out. So let's say the first step is the slow step and the second step is the faster step. And in general chemistry, we don't bother giving you actual rate data usually. We just do it like this and say this one is slow, this one is fast. So the first step is the rate determining step. And remember how we can figure out the rate law of a step. Unlike the overall reaction where you have to do initial rate method stuff or plot concentration over time, you don't have to figure out the rate law of a step experimentally. You can do it just by looking at the equation. So for any general step, AB gives you CD, the rate law equals some rate constant times the concentrations of your reactant raised to a power equal of their coefficients. So here, the rate law should equal some rate constant times NO's concentration squared. It should be second order with respect to NO. So what you should see experimentally is second order with respect to NO and zero order with respect to bromine. And again, you can kind of verify that experimentally using some of the methods we talked about before, like the initial rate method. You double the concentration of NO, you should quadruple the rate. You double the concentration of bromine, nothing should happen. And at this point, you can start to understand why some things can be zero order, because bromine doesn't get involved into a later step. And that step is faster than the other step. And again, so much so that whatever you do to its concentration isn't going to have any effect on the rate. So yeah, it's not part of the rate determining step, so its concentration isn't really going to affect the rate or rate overall. Now, let's say that the second step is the slow step. And it starts off just like before. You get the rate law just by looking at the equation. Here it'll be some rate constant times N2O2 times bromine's concentration. Both of them raised to the power of 1 because the coefficients are 1. But when a later step is the rate determining step, you run into a problem of it probably having an intermediate as part of its rate law, like you see here. And that's a problem because the overall reactions rate law isn't going to have an intermediate in there. So you can't have something in your rate law that isn't part of the overall reaction. It's not going to work out that way. You can't say the overall reaction is going to be affected by the rate of this thing that you don't actually see as part of the reaction. So if you really want to compare oranges to oranges or apples to apples or whatever fruit you kids are eating these days, you need to get rid of the intermediate. And to do that, we actually have to jump ahead a little bit to the next chapter and do a little bit of algebraic magic. So first, the jumping ahead part. We're going to actually go back toward this first step and look at it for a second. So that conversion of NO to N2O2, that step is faster than step 2. So that means that that intermediate is being made faster than the second step can use it. So what should happen is that intermediate is going to start to be built up, and it's eventually going to be built up to the point where it's going to start to react in reverse. So the forward and reverse reactions are both happening in step 1. And what will eventually happen is you're going to establish what we call a chemical equilibrium, where the forward and reverse reactions are occurring at the same rate. And again, more on that in the next chapter, and the chapter after that, and for a while. But for here, all you need to know is that equilibrium means equal rates. So the rate law of the forward direction is going to equal some rate constant. We'll call it Kf for forward, times the concentration of NO squared. The reverse reaction is going to equal some rate constant. We'll call it Kr for reverse, times the concentration of its reactant, which in this case is N2O2. Now again, once they establish equilibrium, and it does happen fairly quickly by our timescales, the forward and reverse reactions their rates are going to equal. So that means that the things on the left are going to be the same thing, which means we can combine these two equations into one mathematical equation, and we can rewrite it a bit where the intermediate is by itself. So the intermediate is equal to all of this other stuff. So at this point, we're going to go back to our rate determining steps rate law, which is equal to some rate constant, which we'll use a little 2 here to show that it's from step 2, times the concentration of our intermediate times bromine's concentration. And just a second ago, we said that the concentration of our intermediate is equal to all this other stuff. So we're going to take that and plug it into our rate laws equation. And all we're doing at this point is just algebra. The rate is equal to K times Y times bromine. Y is equal to all this other stuff. So don't let the chemistry throw you. It's just algebra. Instead of X's and Y's, we use chemical symbols and brackets. So if we plug the equation we got from step 1 into step 2's rate law, that'll give us a bunch of these rate constants times NO squared times bromines. And we can clean it up a little bit by taking all those individual constants and just lump them into one constant that we'll call K. And that'll give us the rate is equal to some rate constant times NO's concentration squared times bromine's concentration. So when the second step is rate determining, what you should see overall is second order with respect to NO, kind of like before. But here, bromine is first order. And again, you can use some of the tricks we looked at before to see which mechanism is the more viable one. Again, both of them are going to be second order with respect to NO. So both of them, initial rate method, doubling the concentration should quadruple the rate. Or if you do it plotting over time, second order is the inverse of the concentration over time. But they both have different orders with respect to bromine. It's 0 order with respect to bromine in the prior method. Here it's first order. So doubling the concentration of bromine will double the concentration of the rate if this mechanism is the correct mechanism. But the point is that we got rid of the intermediate to give us a rate law that does make sense in the scope of the overall reaction. Now the only thing in this rate law are things that are in the overall equation. So again, now you can compare whatever fruit you like to whatever fruit you like. And again, when the first step is the slow step, or did you do it? So when the first step is the slow step, that's the easiest scenario. It's just you look at the step and rate equals whatever. When the second step is the slow step, you got to do a little more work. But it's like a lot of things we talk about. It's the same thing, different reaction. Yeah. Each time you're going to go back to the first step and assume that equilibrium is forming. And again, you do a little algebraic magic to come up with an equation that's equal to your intermediate. Then you go into the second steps rate law and plug that in. So again, you do it a couple of times and you kind of get the hang of it. What are you doing back there? Did he actually? No, I think we're good. Cool. All right, so anyway, that'll be it for now. I'll talk to you guys later. Bye. So, yeah, cool. Thanks. I will let you live another day. Whenever I have an animal in one of my videos, I threaten to kill it. That's not a good habit to get into.